Okay, testing. 1, 2, 3, 4. Testing, testing. Testing, 1, 2, testing, testing. Testing, 1, 2, testing, testing. Testing, 1, 2, testing, testing. Okay, it's 8:01, so let's go ahead and get started. Hopefully you guys can hear me okay. Okay, thank you, Adapong. Okay, we got a lot to cover today. Well, not well, a good amount to cover today. We kind of have to wade through some theory in order to get to some of the good stuff. So I want to get to the good stuff. I want to get to the dessert, but we got to eat our broccoli first. So let's jump right into things. Okay. Let me share my screen. Okay, can everybody see my notes page? Yeah. Okay, I'm sure you'll let me know if you can't see it. Okay, so let's go into 16.3. Okay, 16.3 is the fundamental theorem of line integrals. So let's start writing this out. Okay, so let's write out a formal definition for this. Okay, let C be a smooth curve given by the vector function Okay, so it's a vector function. Keep that in mind. It's like a vector field, okay, or a force field. Okay, the vector function R of t, okay, such that t is going from A to B. Okay, let f be a differentiable function. Okay, now this is lowercase f. Okay. Okay, let f be a differentiable function of the 2 or 3 variable whose gradient vector of a 2 or 3 variable be a differentiable function. Oh, not a. Get rid of the a. Of 2 or 3 variables whose gradient vector capital F equals the gradient of, okay, lowercase f, which is our function. Okay, is continuous on C. Okay, then, okay, the line integral of f dot dr is equal to the line integral, okay, of the gradient of f dot dr, which is then equal to f of r of b minus f of r of a. Okay, so I'm gonna leave that up there for a second, let you copy it down, and then we're gonna go through kind of explain what's going on here, because there's a lot to take in with the notation, okay, and what this is actually describing. Okay, so it says let C be a smooth curve given by a vector function. Okay, so we just have a smooth curve. Okay, we basically have a line integral, right? Okay, R of t, where t goes from A to B. Let lowercase f be a differentiable function. So we're taking the derivative, okay, of lowercase f. Okay, we're actually taking the partial derivatives of lowercase f, okay, to get our gradient. Okay, so don't get confused with the notation here, because I know that in Calc 1, they used uppercase f as the antiderivative and lowercase f as the function, okay, that you're integrating on. Here it's reversed. Here it's completely reversed. We're taking the gradient of f to get capital F. Okay, the gradient of lowercase f to get capital F. So really, lowercase f is the antiderivative, or is the partial antiderivative of capital F. It's reversed here. Okay, so for a lot of students, it's kind of a point of contention on this definition. However, you'll see later on why we use those variables. Okay, we switch them around. Okay, but just think that, okay, we're taking kind of a antiderivative of an antiderivative here. Okay, and we're going to get to what that really means in section 16.4 when we take a double integral. Okay, but for right now, we're keeping it, I don't want to say simplified, or simple, because this is anything but simple. But we're taking it step by step. Okay, so again, based on the fundamental theorem of calculus, okay, but it's just fundamental theorem for line integrals. Okay, let's do a formal proof of this. Okay, let's prove this. Okay, we're going to take the line integral, okay, of f dot dr, okay, equals, okay, and we're setting it up so that the gradient of f is equal to, the gradient of our function is equal to, okay, the function that we're taking our antiderivative of. Okay. Okay, so those two are equal. Okay, so this is equal to the line integral of del f dot dr. Okay. Okay, so this thing is equal to, okay, we're going to go from a to b of del f of r of t. We're going to parametrize this. Okay, r of t dot r prime of t dt. Okay, just like what we've done before. Okay, parametrize this, have our integration factor there of r prime of t dt. Okay, we're going to go from a to b. Okay, now here's where we take our partials. Okay, we want to dot product this. Well, what is the dot product of this? Well, del f of r of t, well, that's the partial derivative of the original f function, that we took a partial derivative of. Okay, so I'm going to write this in vector notation. Okay, so this is going to be the partial on f of, with respect to x, I, the partial on f with respect to y, j, okay, the partial on f with respect to z, k, okay, and I'm going to dot that with, okay, my derivative of r prime of t, okay. So r prime of t is the derivative of r of t, okay. It's going to be, okay, let's just look at the derivative and put this in derivative notation, Leibniz notation. Okay, so again, r of t is r of t is a vector valued function, so it is a vector. Okay, the original f here is a force field. Okay, that's capital F. The original capital F is a force field. We're saying that we're going to allow capital F to be a gradient function. Okay. Okay, but r prime of t is a vector valued function. And so this is going to just be my dx dt, okay, whatever that is, okay, for I, plus dy dt, j plus dz dt, k, okay, and that's all with respect to dt at the very end. Okay, I'm gonna pull this over so I can plug in a dt. Okay, dt right there. Okay, so now this is, okay, a dot product. So what do we do with the dot product? Well, we combine each component, right? We multiply each component together and then we add them. So that's exactly what I'm going to do. I'm going to multiply the I components together, the j components together, and the k components together. So we're going to get partial of f with respect to x. This is d, sorry. This is dx dt. Okay, I plus partial of f with respect to y, dy dtj. Sorry, there are no i's and j's anymore. We dot product. We do the dot product. My bad. Okay, plus df dz dz dt. Okay, from a to b, all with respect to dt. Okay. Okay, well, what is this? What is this thing here? Well, this is just df dt, right? df dt, right? So it's df dx dx dt. Well, this is just the chain rule for vector functions. Okay. So by the chain rule for vector functions, okay, this becomes the derivative d dt, okay, of f of r of t, okay, dt. Okay, so that's by the chain rule. Okay, if I were to take the derivative of this would become the derivative on t of f with respect to x, y, and z component of f of r of t. Okay. Okay. And this is equal to, okay, by the fundamental theorem of calculus, okay, we're taking the derivative and the antiderivative. So what happens when we take the derivative and the antiderivative? Well, they cancel each other out, right? But they don't just cancel each other out because we have a definite integral here. It becomes f of r of b minus f of r of a. Okay, and I'll put my little square, which means QED, which is Latin for quid eros demonstratum, or it has been demonstrated, or we are done. Okay, that's what it means for that one. Okay, number one. Let's do a physics example, since most of us in here are engineers or engineers in training. Okay, let's jump right into physics. Basically, chapter 16 is just it's all the applications to this stuff, double, triple integrals for fluid dynamics and engineering. So it's you know, and then we're going to throw in some Newtonian physics as well, like in this example. Okay, find the work done. Okay, by a gravitational field. Okay, f of x is equal to negative m capital lowercase m. Okay, this is just basically two bodies. Okay, the gravity that is exerted on two bodies. Okay. Okay, negative m, lowercase m, uppercase g. Okay, x cubed, the absolute value of x cubed, or the distance between the two bodies. Okay, cubed times x. Okay, find the work done by a gravitational field, f of x, in moving a particle okay, with a mass lowercase m from a point 3, 4, 12 to the point 2, 2, 0, such that, okay, such that f, capital F of x, is equal to the del of f, okay, or the gradient of its parent function. Just think of lowercase f as the parent function and think of uppercase f as the child function. Okay, del of f, okay, where lowercase f, or my parent function, okay, is equal to mmg over the distance, okay, x squared plus y squared plus z squared. Okay. So basically this is just a plug and play equation, okay, plug and play problem. We want the work done, which is going to be our line integral f dot dr, okay, which is equal to a to b, okay, our point going from a to b of del f, okay, dot dr, which is equal to f evaluated at b minus f evaluated at a, okay. So I just have to figure out, well, what's f evaluated at b? Okay, well, what is b? Well, b is my second point, so that would be 2, 2, 0. This is my point in space, right? My x, y, and z. So this is going to be f equals, okay, mmg. So I should make my m a little bit bigger. mmg over the square root of 2 squared plus 2 squared plus 0 squared. Okay, so this is going to be mmg, mmg, over, this is going to be the square root of 8, which is 2 radical 2. Okay. Okay, so that's f of b. Okay, so what's f of a? F of a is going to be f of 3, 4, and 12. Okay, so f, okay, I guess I should put a b here. And an a there. F of a is equal to mg over the square root of 3 squared plus 4 squared plus 12 squared. Okay, this comes out to 9 plus 16, which is 25. 25 plus 144 is 169. The square root of 169 is a perfect square. This comes out to mg over 13. So this is equal to f of b minus f of a, which is equal to I'm going to factor out the mmg's. Okay, mmg times 1 over 2 radical 2 minus 1 over 13. Okay, so they gave you what the parent function was, what made it real nice. Okay, didn't have to derive that. We're not going to be so nice on the ones to come. Okay, they did derive this function back in 16.1. It's not something they're really going to be tested on, but if you want to reference back to 16.1, they did derive that vector field, okay, that force field. Okay. Okay, let's go on to a lot of definitions now. Okay. So theorem. Okay. Okay, the line integral f dot dr. Okay, over C is what we call independent of path. Okay. If and only if our independent path in D, okay. That's our domain in our domain D. Okay. If and only if, okay, the line integral for C, f dot dr is equal to 0. Okay, so independent of path means that the whole thing is equal to 0. Okay, so the total line integral equals 0. Okay, for every closed path C in D. Okay, closed path. What's a closed path? Closed path is a circuit. Okay, think of a racetrack as a closed path. Okay, so every time we go around the racetrack, okay, that's a closed path. You have a starting spot and you have an ending spot. Okay, if after I go around this entire line integral, okay, all of the paths add up to 0, okay, all of the integrations add up to 0, meaning that it was just as high on one side as it was low on the other, okay, then we say that this is independent of path, meaning that it doesn't matter which direction you go, you're going to end up with the same result. Okay, so let's look at this guy here, this path that I drew. Okay, this, let me go back. Try to make this a little nicer. Clean this up a little bit. Okay, there we go. Okay, so I'm going to call this C1. I'm going to call this C2, okay? Okay, so two paths. C1 and C2 are kind of subpaths of the entire C. Okay, so C1 plus C2 equals C. Okay, for the entire closed path. Okay, I'm just saying, hey, if I break up C1 and C2, okay, they should equal C, right? Okay, and if the line integral over C is equal to 0, then no matter how I add up C1 and C2, it should equal 0. Okay, so if I take the integral along path C1, and then I add the integral along path C2, those should add up to 0. Well, the way that we write that is the integral of path C1, okay, of f dot dr minus, okay, the integral of path C2, f dot dr is equal to 0. Okay, thus implying that the integral of C1 f dot dr is equal to the integral of C2 dot dr, f dot dr. Okay. 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 So we just say that it's independent of path if, okay, we get the same result regardless of how we break up our paths. Okay. Doesn't matter. I could be going forwards around the whole thing. I could be going backwards around the whole thing. It doesn't matter as long as we add up. And we could have as many C1, C2, C3, C4, C5. We could have as many of these little chunks as we want as long as they keep breaking up and adding, okay, to the entire path. Okay, let's do another theorem. Suppose F is a vector field that is continuous on an open connected region D. Okay, open connected region D. So it's connected, okay, D. We didn't really talk much about D in the last one. We will get to that. D is the enclosed area, okay, around the line integral. So think about the line integral, it's being closed, right? And so D is what is being enclosed. D is, it's kind of like if you had a racetrack around a lake, the D would be the lake. Okay. So suppose F is a vector field that is continuous on an open connected region D. Okay, if go over here, if F, nope, that's not what I want. If the line integral of F dot dr, okay, is independent of path, okay, so we saw how we needed to define what independence of path is in order to use this theorem. Okay, independent of path in D, then capital F is conservative okay, is conservative on D. Okay, it's a conservative vector field on D. That is, there exists a function lowercase f such that del of f, the partial derivatives of f, okay, the gradient of f, okay, is equal to capital F. Okay, in other words, okay, we could say that, okay, C1, the gradient of f with respect to C1 dot dr is equal to the gradient of f dot dr with respect to C2. Okay. Okay, so conservative, that's the word that we really want to focus on today for the rest of this lecture. Okay, is conservative. What does it mean to be conservative? Conservative is not a political position. Okay, conservative is with respect to conservation of energy. Okay, conservation of matter, conservation of mass. Okay, conservation of momentum. That's what we're talking about, conservative here. Is it conservative? Is it conserving these properties, okay, in physics that we want to conserve? Okay, so that nothing is created and nothing is destroyed. Okay. Okay, so again, if it's independent of path and it's continuous, okay, if it's independent of path and it's continuous, okay, then there exists a parent function who is also continuous. Okay, the parent function is also continuous. Okay, such that we're just basically saying, look, the parent function exists. If the parent function exists, okay, we're saying that f exists, little f exists, okay? Little f exists. It means that we can get a function whose gradient was capital F. That's really just what it means here. It says we can get the parent function, okay, f of t, basically f of x, y, z, however you want to do it. I'm just going to leave it as f. Okay, we can get the parent f, okay, from, okay, capital F. We can get the parent f from capital F by, okay, figuring it out. Okay, and we'll get to what does that mean? How do we figure that out? Maybe we'll do that right now. Okay. Let's see. Yeah, let's do that. Okay. Let's do number 1 here. Okay, given that f of xy equals 3 plus 2xy I plus x squared minus 3y squared j is continuous, okay, and independent of path, find lowercase f. Okay, so we want to find lowercase f. Okay, we said this continuous independent path. So we know that a lowercase f exists. Okay, we need to find f such that the gradient of f is equal to f. Okay, so we want the function whose gradient is equal to my vector function here. Okay, I want the gradient, the function whose gradient is equal to the vector valued function, okay, f. Okay, so how are we going to do this? Well, I think we've done this in the past before when we talked about gradients, okay, and we want to go backwards, okay, so we're going to take this piece by piece. And we're going to say, oh, well, what is del f? Okay, del f would be, okay, this would be equal to f sub x, okay, the partial with respect to x, I, plus the partial with respect, partial with respect to, think about this for a second. Yeah, partial with respect to y, j, there we go. Okay. Okay, so we want f sub x to be equal to 3 plus 2xy, And we want f sub y to be equal to x squared minus 3y squared. Okay. Because this is supposed to, again, equal capital F. Right? So we want the partial derivative of x to be equal to 3x. So we're going to have to take an antiderivative on this one. Okay, let's take an antiderivative with respect to x only. Okay, so this becomes 3x plus x squared y. Okay, that's my antiderivative. Okay, plus some value of y plus some constant. Okay, plus some constant. Because that function of y could have gone to 0. Okay, if I took a partial on x. Okay, what about f sub y? Well, same thing. This is x squared y minus, okay, this is going to be y cubed, okay, plus, okay, we'll call this h of x plus k. Okay. Okay, so we want the whole thing. We want the whole parent function. Well, what's the whole parent function here? Okay, f of x sub y. Well, it looks like we have x squared y squared is what they have in common, right? So x squared y, oh, sorry, x squared y, not y squared, is what they have in common. They have a function of just 3x, which is my h of x. Okay, so that's 3x. And then they have a function of gy, which is just my negative y cubed. Okay, and then plus k, okay, from my constant. Okay, I could have called this k1 and k2 and just left it as a k. And that's it. Okay. Okay. Okay, let's go into more theorems here. Okay. I'm going to try to use a bunch of these theorems. A lot of theory this morning. Okay, theorem. Okay, if f sub xy equals p xyi plus q xyj is a conservative, okay, conservative. What's conservative mean? Means that there exists, okay, then f is conservative. That is, there exists a function such that such that del of f is equal to f. Okay, that's what you want. Conservative equals that. Just means, look, we can find a parent function. That's all it means, is it's conservative. Okay, if it's not conservative, we can't really do much because we can't go backwards. Okay, is a conservative vector field. Okay, where P and Q have continuous first order partial derivatives on a domain D, then throughout D, we have the partial of P with respect to X, or sorry, with respect to Y, is equal to the partial of Q with respect to X, okay? So very important theorem, okay? It says that, look, if it's conservative, then dP dy equals dq dx. If it is conservative, then the partial of y on y is equal to the partial of x. And we've seen this before, okay, saying that, okay, if, okay, so remember that the del of f is equal to f, right? Del of f is equal to f, right? So what would we do? We would take, okay, we would take what? We would take, okay, whatever the original function was, right? Okay, so we're saying that p of xy is f sub x. Okay, and then we're saying take this guy and do what with him? Take this guy and then do a partial with respect to y. So that's f sub x sub y, right? F sub y x, okay, is equal to q of xy, q of xy, right? So we want the partial, okay, the partial of p, okay, and here now we want the partial of q with respect to x. That's f sub y, right? Because it would be del of f, so we would take the partial, because it's the j value, that's the y value, okay, the y component, okay, of the vector field, and say, oh, okay, so the y component of that, we're going to take our partial with respect to y, and then we're going to take our partial with respect to x. And you can see that basically we would end up with, okay, f xy is equal to fyx. And where have we seen that before? Well, we saw that before when, okay, when f was continuous. If it's a continuous function, it's a really nice function. Okay, it's continuous, then that is true. Then when we take our second order partial derivatives, x, y, yx, they are equal if the original function was continuous. Okay, so just some goodness there. Okay, that's gonna this is gonna become very important to us in a minute. Okay, let's define what a simple curve is. Okay, a simple curve is a curve that does not intersect itself. Okay, we want to deal with simple curves. We do not want to deal, okay, with this guy here. That's bad. Okay, no figure eights allowed. Okay, we want to deal with a simple curve, okay, where it's the air, like going around a lake. Okay, no figure eights, no, okay, curves that, you know, intersect each other twice or three times, or it gets messy. Okay, we don't want this either. Okay. Okay, a simply connected region is a region, is a connected region. Okay, connected. What does connected mean? Okay, again, we do not want this. These are regions. They're not connected. Okay, they're islands. Okay, they're not connected. Okay, we want a simply connected region. Okay, simply connected region is a connected region. So you could have a connected region. Okay, this is a connected region. They're connected by, here, the problem is that, okay, they're not simple curves. Okay, so we probably don't want that either. This is a connected region such that okay, every simple curve, simple closed curve in D encloses only points that are in D. Okay, so what does this mean? It means that, okay, this is a great one. This, okay, you would think, oh, that's nice. No, because we're going to have holes. It's going to be like Swiss cheese. Okay, oh, look at that. It's not, no longer is it simply connected. Okay, region. It's not a simply connected region. We just want, okay, we're making definitions of these things, right? What's a simply connected curve? What's a simply connected region? Okay, we don't want holes in our region. Okay, we don't want crossings in our curves. If we have no crossings in our curves and no holes in our regions, then we can do some nice math. So we kind of have to eliminate, okay, what we do want, okay, exclude, sorry, we want to eliminate what we don't want, we want to exclude what we don't want, and opt for what we do, okay? So this is not simply connected, okay? Okay. So now we've set it all up, okay? Set it all up. Okay. For the last theorem that we're going to talk about in this section, okay, here's the setup. It's been a long time coming. Here's the kind of the piece de resistance, okay, the crescendo of the theorem that we want to lay out, okay? So it says basically if everything is nice, we have, you know, those kidney bean shapes that we put up here, okay? Kidney bean shapes like swimming pools, right? So think of your swimming pool, okay? Your local swimming pool, or okay, kidney bean shape. Okay, if we have these nice things happening, okay, then we can do some nice math. If we have anything other than those nice swimming pool figures, we can't do some nice math. But those swimming pool figures are ones that we really want anyway, because when we're talking about fluid and fluid dynamics, okay, we are going to let the fluid, okay, flow wherever we want it to go. And generally, because of the cohesive nature of water and fluids, and they tend to stick to each other, we're not gonna end up with those scenarios that we don't want. Okay, let F equal Pi plus Qj be a vector field on an open, simply connected region D. Oops. Okay, suppose P and Q have continuous first order partial derivatives and dp dy equals dq dx throughout D, then F is conservative. Okay, then F is conservative. So what we just set up was a test for conservation. Okay, we just set up a test for conservation. That was the whole premise to what we just did in the last half hour. Okay, we set up the criteria, and if this criteria holds, if this world holds that we just created, then F is conservative. Okay, if we have a simply connected region, if the first partial derivative with respect to y of p and the partial derivative with respect to x of q, if those are equal, then we know that F, the vector field, is a conservative vector field. It is a vector field that has conservation. Okay. Okay, let's do number 2 here. Actually, did we do? I think we did number 1 twice. Yeah, this should be number 2. Okay, and this should be 3. Okay. Okay, number 3, determine if the vector fields are conservative. Okay, are the vector fields conservative? Okay, and why is conservation important to us? Because it means that we can take the line integral of it with respect to the fundamental theorem of line integrals. Because if F is conservative, okay, if F is conservative, then, okay, then F is conservative, then, comma, okay, after this, then there exists a parent function for that function. Does that make sense? Then there exists a del F equal to capital F. Okay, means that there is a parent function there that exists, and we can take the line integral with respect to the fundamental theorem of calculus. Well, the fundamental theorem of line integral calculus. Okay. Okay, so this is a test. This is a test for, can you use the fundamental theorem? Okay, if you can, if it's conservative, then we can use the fundamental theorem. If it's not conservative, all bets are off. Okay, we'd have to test it some other way. So determine if the vector fields are conservative. A. Okay, f of xy equals x minus yi plus x minus 2j. Okay, so what are we going to do? Well, we're going to use our little handy dandy equation right there. Okay, that says, look, the partial on y of p, well, what's p in this case? It's x minus y, right? Okay, what's the partial on y of this? Well, it's -1. Is that equal to the partial on x of x minus 2? Well, what's the partial on x of x minus 2? It's +1. Are those equal? Nope. So not conservative. Okay, not conservative. So it's probably not, it probably doesn't have continuous parent function. Okay. Okay. So again, just a test for conservation here. Okay, B. Okay, let's do f of x sub y is equal to 3 plus 2xy I plus x squared minus 3y j. Okay, is this guy conservative? Well, let's see. D dy, okay, partial on y of 3 plus 2xy. Okay, this becomes 3y plus xy squared. No, I don't know what I'm doing. I'm integrating. I need to be differentiating. This just becomes 2y. No, 2x, I'm sorry. It becomes 2x. Okay, okay, what about this one with respect to x? Okay, this is x squared minus 3y. So take the derivative with respect to x here. That's 2x. Look at that. Lo and behold, 2x is equal to 2x. So what do I know? I know that these are equal. Okay, which means that they're conservative, which tells me that del f can equal f. There is a f such that that can equal f. Well, duh, we already figured it out, right? We already did this one. That was example 1. We found f already. What was f? F was equal to, I think it was xy squared, right? What was that? Xy squared. Y squared plus 3x minus y, right? Plus k. We found this guy already, and it says, hey, look, that's it. This is able. We're able to get that. I mean, it'd be kind of nice to know at the very beginning if we're able to get something or not. And that's what this is. This is a test to see if we can go backwards. Okay, by going forwards. If we take our second order partial derivatives, then we can go forward. If they're equal, if going forward they're equal, then we can go backwards and get the parent function, if that makes sense. Okay. Okay, which leads me to example number 4, which is exactly what we're going to be doing. Okay. Okay, we're going to put all these pieces together. Okay, and example 4 here. Okay, we'll put all the pieces together. If, okay, f sub xy equals 3 plus 2xy I plus x squared minus 3y squared j. Okay, if f is equal to this, okay, then find the line integral, okay, f dot dr, where c is the curve, okay, r of t, oops, r of t equals e to the t sine t I plus e to the t cosine tj, where t goes from 0 to pi. Okay, period. Okay, so we're gonna find the line integral over c, okay, of this curve. Okay, and basically we're saying, look, can we use the fundamental theorem or not? Okay, so what do we know? Okay, well, let's test for conservation. Okay, let's test to see if this is conservative. Okay, 1, is it conservative? Well, is d dy of p equal to d dx of q? Yeah, 2x equals 2x, so it checks. It is conservative. That's good. It means that, hey, we're in really good standing for okay, finding the line integral with respect to the fundamental theorem of calculus. Okay, 2. Okay, 2. Here, I want to find the f. Okay, find the parent function f such that, okay, del of f is equal to uppercase f. Okay, find the parent function. Well, we already did that. That was example 1, I believe. Okay, we did this, right? We found the parent function. What was the parent function? The parent function, okay, was f of xy equals, it was x squared y. What was it? It was x y squared. Yeah, xy squared plus 3x minus y cubed plus k, right? Now, once we found that, okay, those two pieces, is it conservative? Yes. Okay, so conservative is good, therefore a parent function exists. Okay, now that we know the parent function exists, find the parent function. Okay, now that the parent function, we know what the parent function is, now we want to find the line integral. Okay, so f dot dr, okay, the line integral, f dot dr of this thing, okay, is equal to c, the gradient of lowercase f dot dr, okay, is equal to f of b minus f of a, right? F of b minus f of a. Okay. So I'm going to rewrite this as f of r of b minus f of r of a. Okay. So, well, what is this? What's b and a in this case? Okay, b and a, what are my limits? What would be my limits of integration? Well, this would really be a function on t, right? And so where is t going from? Well, t is going from 0 to pi, right? Isn't it going from 0 to pi? So this would be f of r of pi minus f of r of 0. Okay. So now I have to evaluate, well, what's f of r of pi? Well, what's r? R is this function here. Okay, so what's r evaluated at pi? Man. Okay, so r of pi is equal to, let's plug in pi here. Okay, e to the pi sine pi I plus e to the pi cosine pi j. Okay, evaluating this, sine pi goes to 0, right? Cosine pi goes to -1. So I'm left with 0, -1, or sorry, negative e to the pi. So I'm going to write this as a vector in component form. Vector is 0, comma, okay, negative e to the pi. Okay, so now let's do r of 0. What's r of 0 going to be? This is e to the 0 sine of 0, I, that's still going to go to 0. Okay, plus e to the 0 cosine of 0. That thing's going to go to 1, j. So component form is 0, 1. Okay. Okay, so now let's evaluate f of r of, okay, f of, so this is equal to, or this is kind of a parenthetical thought, okay, to get those guys. This is equal to f of 0, negative e pi minus f of 0, 1, right? So kind of think of it like that. Okay, now what was f? F was our original function, right? So wouldn't these be my x's and y's, right? Wouldn't these be my x and y values that I'm going to be plugging into my function? Yeah. So let's just go ahead and do that. Let's plug in. Okay, this is going to be, every time I see an x, isn't that going to give me a 0? Right? Every time I plug in x here, isn't that going to give me a 0? So really, isn't it just that the term that has y is going to survive? Y and y only, right? So this term here is going to survive. Why is the constant not going to survive? Yeah, the constant's not going to survive because we're going to end up subtracting it from itself. And so the constant isn't going to survive. The 3x is not going to survive, and the x is not going to, the xy squared is not going to survive, right? So what are we going to get here? We're going to get the negative of a negative e pi cubed, right? Minus the negative of 1, okay, just plug in the y values, 1 cubed. Okay. So this negative cubed is going to be a negative, times the negative is a positive. This I can rewrite as e to the 3 pi. And this is a negative. This is going to be 4 negatives, which makes a positive. So plus 1. That's it. Done. Okay. Okay, let's jump into why this is called conservative. Okay, where's this conservation idea coming from? Okay, and what we're going to do is we're going to prove the conservation of energy right now. Okay, so don't freak out, it's not that hard. Okay, but we're going to prove the conservation of energy. Okay, potential and kinetic energy. Okay, so proof of the conservation of energy. Okay. 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 Yeah. Okay, so we have force equals mass times acceleration. That's Newton's second law of motion, right? Everybody knows that one. Okay, in vector form, this is going to be F r of t is equal to m. Okay, and if r of t is my distance, then how am I gonna represent my acceleration? Yeah, with a second derivative, right? So this is going to be the second derivative of t. Okay, that's my acceleration. So the work done is going to be a line integral, okay, moving the position over with a certain amount of force through a force field, okay, dot dr equals, okay, from A to B of f r of t dotted with r prime of t dt. Okay, so what is this going to be equal to? Well, we're going to replace the f of r of t with m r double prime t. So this is A of b, m r double prime of t. dot r prime of t dt. Okay, this is equal to, I'm going to pull out the m, okay, and I'm going to do a little trick here. I'm going to be a little sneaky. Okay, and then I'm going to write two of the same thing so that I can use the product rule. Okay, so I'm gonna write two of these guys. So I'm gonna take a 1/2 of r double prime of t dotted with r prime of t plus r double prime of t dotted with r prime of t. Okay, dt. Okay, cool. I'm going to pull out the 1/2 in my next step. So this is 1/2 m. Okay, now, what is the rest of this stuff? Well, the rest of the stuff is just the product rule. This is the product rule for vectors. Okay, and we dot product these. Okay, and so this is the product rule. This is the derivative of the first times the second plus the derivative of the second times the first. Well, what would create a double prime as a derivative? Wouldn't that be a single prime, right? My first derivative would create a second derivative, right? So the derivative of the first would have had to have been, the first would have had to have been r prime. Oh, okay. Dotted with r prime itself. Oh, okay. And this again is from a to b, okay, of dt. Okay. So this is going to be 1/2 m, okay. This guy here, I'm going to rewrite him as, okay, r prime, okay, of t, okay, t squared. Prime of t. Okay, it's the magnitude, okay, of r prime of t, okay, squared. Okay. Okay, from a to b, dt. Okay, let me just make sure I'm doing this correct. Oh, you know what? I forgot this guy here. My bad. I was like, I knew I dropped something. Okay, so this thing here has a ddt. Okay, why is that? Why is there a ddt there? Because to take the product rule, I would have had to take the derivative. Okay, so that's, I dropped that there. Sorry about that. Okay, so this is ddt. Okay. Okay, does that make sense? We take the product rule of this guy here, okay, of r prime t dotted with r prime t, take the derivative of that with respect to t, and that gives me this one. So I had to have put the derivative here. Okay, which is what I want now is I want to be able to use this, okay, and we're going to use the fundamental theorem of line integrals, okay, to evaluate this now. We're taking the derivative and antiderivative, and so by the fundamental theorem of line integrals, this becomes r prime, okay, of a or b, sorry, r prime of b squared minus 1/2 m, okay, r prime, okay, of a squared. Okay, and what would be What would be R prime? How would you describe R prime in terms of kinematics laws? Okay, what would be R prime? Would it be distance? Would it be acceleration? No, it would be velocity, right? Wouldn't that be velocity? R prime, that would be the first derivative, right? The first derivative of my displacement vector. Okay, that would be the velocity. So this becomes 1/2 m v sub b, okay, minus 1/2 m, or v squared sub b, minus 1/2 m v a squared. Oh, okay. Well, isn't this just kinetic energy? Yeah, this is kinetic energy. So this is kinetic energy at B minus kinetic energy at A. Oh, okay. Kinetic energy at B minus kinetic energy at A. Okay. So now let's talk about the potential energy. Let's take a take a break at the kinetic energies. Let's switch to potential energy. Okay. So how are we going to deal with potential energy? Okay. And again, what was this equal to? This was equal to the work done, right? Work done is the difference in the kinetics. Okay. Now what about the potentials? Okay. Well, the potential energy in 3 space is equal to negative its position in 3 space. Okay, potential energy is related to its position, right? The higher I go up, okay, away from the Earth, the more potential energy I have, because the force that's pushing that, the potential energy, okay, counteracts the force that's wanting to counteracts gravity, which is the force that's wanting to push me down. And so it's a negative. It's in the opposite direction of the force that's wanting to go. Okay, so it's negative of the position that I'm at. The higher the position, the more, okay, the more potential energy I have. Okay, if F is equal to del of F, then F is equal to negative del of P, negative del of P, where P is the potential energy, and the work done is then equal to the line integral of the force field dot dr, which is then equal to negative del P dot dr. Okay. And by the fundamental theorem of line integrals, okay, this is just going to be equal to negative P RB minus negative P RA. Okay, so distributing, the negative, well, not distributing, but combining the negative here and reversing the order, I'm going to get P evaluated at A minus P evaluated at B. Okay, and so what is that? That's, again, the work done. So let's set these two equal to each other. Let's set the kinetic energies equal to the potential energies. Okay. So I'm gonna start with the potentials. PA minus PB is equal to KB minus KA. And I'm gonna put all the A's on one side and all the B's on the other. So push that over there and push that over there, and what do we get? We get the potential energy at A plus its kinetic energy at A is equal to the potential energy at B plus the kinetic energy at B, which is the law of conservation of energy. Boom. It's happy. We'll make it a sun because that's where we get our energy, right? Okay. It's nice. Nice stuff. Okay, good stuff. Okay, that's why it's called conservative, if we can utilize those properties. Okay, let's move into 16.4. Okay. Okay, 16.4 is called on something called Green's theorem. Okay, so what does it mean to be positively oriented? Positive orientation. Okay, of a simple closed curve. C refers to a single counterclockwise transversal of C. Okay, counterclockwise. What does that mean, counterclockwise? It means that we're going around opposite the way the clock would be going, and we're transversing the entire thing. It's this direction. Okay, again, we use the right-hand rule. Okay. Okay, right-hand rule. Think about your thumb pointing up. Okay, which way are your fingers curling? Right? So thumb is pointed up. Okay. Okay, whatever. Okay, your fingers are curling. Okay, and your thumb is up. So the way which it's curling is the positive orientation. It's positively oriented. Okay. That's what it means to be positive oriented. Okay, let's talk about Green's theorem that uses the positive orientation. Okay, Green's theorem. Okay, let C be a positively oriented, piecewise smooth closed curve piecewise smooth, simple, closed curve. It basically says nothing weird. Okay. In the plane. And let D be the region bounded by C period if P and Q have continuous partial derivatives on an open region that contains D, then the line integral of C of P dx plus Q dy equals the double integral over the region D of the partial Q with respect to X minus the partial P with respect to Y over the area. We're taking the boundary of the area and turning it into a double integral over the area. It's kind of amazing. Okay, now what does this little circle in my line integral mean? Okay, that little circle just tells me that it's a positive oriented line integral. Okay, so this means positive orientation. That's all it means. That's all it means, is that it's positively oriented. That's what that little notation means there. Okay. Okay. So we want to evaluate this line integral over C of x to the fourth dx plus xy dy. Okay. Where C is the region or sorry, D. No, C is the, it's not the region, it's the boundary of the region given by the points 0, 0, 1, 0, and 0, 1. Okay. I'm going to evaluate this using Green's theorem. Okay, because it's a lot easier using Green's theorem than trying to evaluate it without it. Okay, especially since we have the setup. We have the setup dx dy. Okay. Okay, so what does this region look like? Well, the region is a triangle, right? Okay, and what we're saying is as we go around this triangle, okay, the line integral around this triangle, okay, of x to the fourth dx plus xy dy, okay, the line integral around this thing is the same as the double integral over that region where we have dq dy dx minus dp dy. Okay, so that's what we're wanting there. Okay, so we want the double integral, okay, which is, it's amazing. It's just amazing. It turns something linear into something two-dimensional. It's just kind of is amazing. Okay, so to think about it. Okay, so well, let's do the inside first. Okay, so this is dA. Okay, this is Green's theorem here, that this line integral is going to be equal to this. So what is dq dx? Okay, dq dx, well, what is q? Q is xy. So take the derivative with respect to x and we get y, right? Okay, what about dp dy? What's that? Take the derivative of x to the fourth with respect to y, that's just 0. So we're going to get a double integral, okay, of y minus 0, okay, and I'll do a dy dx here. Okay, so now what about our limits? Our limits of integration over d. Okay, what are our limits going to be? Well, our limits, okay, we're first taking our slices over d with respect to y, right? So this is a line, okay, this goes from 0, okay, this goes from y equals 0, this bottom here, to this line. What is this line? Well, isn't that line a slope of -1 with a y-intercept of 1? So wouldn't that be just 1 minus x, right? Wouldn't that be y equals 1 minus x? So that's 1 minus x. And then what would my x values go from? Well, my x values go from 0 to 1. 0 to 1 of y dy dx. Okay, so let's just integrate this. Y squared over 2, 0 to 1 minus x. This becomes 1 minus x squared over 2. Integrate that from 0 to 1. Okay. dx, we could do a u sub on this, or we could factor or multiply it out. It doesn't matter. I'll do a u sub. U is equal to 1 minus x. Du is equal to negative dx. So negative du is equal to dx. Okay. So this is going to go transfer my limits, right? So u of 1 is equal to 0. U of 0 is equal to 1. Okay, so this goes from a 0 to 1 of negative du. So this is going to be negative u squared over 2. Sorry, it's not 0 to 1. It's 1 to 0. Okay, negative u squared over 2 du. Okay, well, I could reverse the limits of integration and get rid of the negative if I really wanted to. Okay, so this would be 0 to 1, okay, of u squared over 2 du. Okay, this is going to be u cubed over 6 from 0 to 1, and then plug in the 1 and 0, we get 1/6. Boom, nice. Okay, so the line integral over this region ended up being 1/6. Okay, turning that line integral into an area problem. Okay. Okay, let's do another one. Okay, number 2. Okay, evaluate, okay, the line integral, positively oriented line integral of 3y minus e to the sine x dx plus 7x plus the square root of y to the fourth plus 1 dy to 7. Okay, where C is the circle x squared plus y squared equals 9. Okay. So let's see what we got here. Okay, we want to turn this into a double integral using Green's theorem. Well, again, what is Green's theorem? Okay, it's dq dx minus dp dy. Okay, so what's dq dx here? What's the integral of q, but only with respect to x? Well, it's really nice because everything that didn't involve something nasty goes away, and only the 7 is left over. Okay. Okay, and then what about dp dy? Well, dp dy, again, everything that's nasty goes away, and all the stuff that's not nasty is left behind, and so this is just minus 3. So that's 4. It's just a whole number, 4. That's kind of cool. Okay, so this is going to be the double integral over d of 4 dA. Okay, the double integral of 4 dA. Okay, well, what is my d? What is my d in this case? My d is my region, the domain here, which is just a circle of radius 3, right? It's a circle of radius 3. Okay, so r equals 3 and theta is equal to 2 pi. Well, how am I going to evaluate this with r equaling 3 and theta equaling 2 pi? Well, yeah, I'm just going to turn it into polar coordinates, right? I'm going to do my 4r dr d theta. Remember, it's laughing at you. R dr, hardy har. Okay, 4r dr d theta, right? From 0 to 3 and 0 to 2 pi. Let me get rid of the d here. Okay, so this becomes 2r squared evaluated from 0 to 3. Okay, that becomes, plug in the 3, that's 9 times 2, which is 18. Integrate that from 0 to 2 pi d theta, and we just get 36 pi. Okay. Okay. The area of a region D, okay, so the area of a region D, let's think about this for a second. The area of a region D, okay, can be computed okay, so the area of a region D, dA, right? So isn't that's the area of the region, right? Because we would just have, to find the area of the region, wouldn't this just be 1, right? So our function would be 1, okay? dA, right? Okay, this is equal to the area, can be computed, okay, using Green's theorem. Okay, can be computed using Green's theorem. Okay. Where d q x minus dp dy would have to equal what? What would this have to equal? If we go back to Green's theorem, what would this have to equal? Yeah, it'd have to be this 1 here. Okay, it'd have to equal 1. Okay. Okay, so there's a couple of ways to get this to be equal to 1. Okay, a couple of the easiest ways are to just have a function involving x. Okay, so we could have a line integral that involves only x, and then dy. Okay, so we took the partial of this is going to be a q with respect to x, right? There's no dx term, there's no p term, there's only a q term in this, and that's going to go to 1. Okay, okay, so that's one way to do it. Okay, or okay, the line integral y dx, that's another way to do it, is to have this go to 1. Okay, or the more complicated version is 1/2. Okay, 1/2 of x dy, okay, minus y dx. Okay, now why does this work? Okay, well, if we take Green's theorem here, we get x dy, that's going to be 1, right? Okay. Oh, sorry, this is a negative here. My bad. Okay, this is a negative. This is going to be 1, right? If I do negative dp dy, right, negative dp dy, then we get negative of a negative, which is positive, and that's going to be 1. So this is going to be 1 plus 1, which is 2, and then divide by 1/2, we get 1. Okay, so that's the deal there. Okay, okay, so we're going to use this to our advantage in the last problem here. So we want to find the area. Find the area of the ellipse x squared over a squared plus y squared over b squared equals 1. We want to find the general formula for the area of an ellipse. Okay, what's the general formula for the area of an ellipse? Well, let's use Green's theorem to help us figure that out. Okay, so I'm going to use Green's theorem kind of backwards. Okay, we're going in the reverse order for Green's theorem. We're turning this double integral into a single integral. Okay, dA, okay, is equal to, okay, 1/2. I'm going to use that last one here. 1/2, okay, positively oriented. We're going to take the ellipse and we're just going to make sure that it's positively oriented. That's fine. We can go around an ellipse any direction. I just want to go around in a positive orientation. Okay, let's go around the ellipse positively. Let's keep things positive. I'm a positive person, so let's keep things positive. Okay, so 1/2. Okay, positive orientation, dy minus y dx. Okay. Okay, so now let's parameterize this this equation. Okay, in terms of a single variable t. Okay, so what's x going to be equal to? X is going to be equal to a cosine t. Okay, and what's y going to be equal to? Y is going to be equal to b sine t. Okay. What's dx going to be equal to? Dx is going to be equal to negative a sine t. Now what's dy going to be equal to? Well, it's going to be equal to b cosine t. Okay, okay, nice, nice. Okay, we could use theta if we really wanted to. I'm just using t just for simplicity. Okay, so a and b are variables, but we don't integrate over a and b. We only integrating with respect to t here. Okay, so this equals 1/2 of the integral of x. Well, what is x? X is a cosine t times dy. Well, what's dy? dy is b cosine t minus, well, what's y? Y is negative, or sorry, y is b sine t times dx, which is negative a sine t. Okay, dt. So what is this going to equal? Well, this is going to be equal to ab cosine squared t plus ab sine squared t. You might be able to see where this is going. Okay, this equals 1/2 the integral of, okay, ab, factor out the ab, we get cosine squared t plus sine squared t, which goes to 1 dt. Okay, and so what's t going from? If t is our angle, right? If t is our angle here, what's our angle going through? Our angle is going from 0 to 2 pi, right? So 0 to 2 pi. So this is 1/2 the integral of ab dt from 0 to 2 pi. So this just becomes 1/2 abt from 0 to 2 pi. Plug in our 2 pi and 0 for t, and we get 1/2 ab times 2 pi. The 2's cancel out, and we're left with ab pi. And that is the area of an ellipse with axes minor axes length AB, major axes length, 2AB, 2A and 2B. Okay, so basically, if I know what the major and the minor axes are, I take half of those lengths, multiply them together, and then multiply by pi, and I get the area of an ellipse. This is the area of an ellipse. Okay, now what if A and B were the same? What if A and B were the same length here? A and B were the same length, right? Well, what would we call that? Well, we call that a circle. We would call that, right? We would say that A and B are the same length. The major axis and the minor axis are the same. And so we would get R's here. And so the A would be equal to pi R squared. Look at that. There's a proof. There's a nice proof for the area of a circle. It took thousands of years to prove. Okay, that's just another nice proof of them. There's